of explaining our AI robotics final project, which was a Trackmania AI bot that would be able to complete any track at a speed that is unable to be achieved by a regular human. This goal that we had at the start was highly ambitious. There were a few resources on YouTube that kind of said that it was possible, but we quickly found out that the scope of the information that we could extract from the game using a plugin was much more limited than we first thought. So we pivoted our goal to be training onto one specific track that was highly difficult, massive amount of turns, a track that would be difficult for a human to drive. We wanted our bot to be able to drive it, and relatively quickly. Again, we ran into issues with how the actual bot could interpret the map. We attempted to extract a spline based off the 3D location of the blocks of the track in Trackmania. But again, this is converting a native Trackmania file into binary and then turning that binary into a mathematical path. This didn't work well. It was going to take a colossal amount of processing power and computational cost, which is something that we simply couldn't afford in the time frame it was to complete this project. So we pivoted. The pivot was we would set a run that we would record the position of the car periodically throughout the run. This position would be the XYZ and also the yaw of the car. This would allow us to set a gate that would be not only the position of the car, but also at the vector in which it passed through. It would follow the path, ideally, get through all the gates, and then finish the run and slowly optimize to get quicker and quicker. The observable space of the car would be its speed, yaw, pitch, roll, the position globally, so the XYZ position, and then also it would read the gates that we'd set. So the gates would be XYZ, the distance to the gate progress, so how many gates it's gone through out of the total gates, the previous steering angle, the previous gas, and then the previous brake. This 14 float array is much more complex than the one that we did for our previous project. So again, computational costs were high, but we still expected it to be able to run through. We set our hyperparameters very similar to the last PPO agent, so a learning rate of 0.0003. The number of steps would be 2048, the same as what we did last time. The batch size, 256, the same. The epochs is 10, so it loops 10 times per update. The gamma was 0.99, that's just the industry standard one that we found. And then our entropy coefficient was 0.01, which is our random chance to drive through the track. We were able to achieve a bot that could drive the track. It was able to complete a synodal type track that we thought would be best for training. We ran into issues in its interpretation of our reward structure is because it doesn't know what walls are, it wouldn't try to avoid walls. It would just see them as an area that slows you down. So we tried to add crash detection in terms of if a certain speed barrier was hit negatively within a single time step, which is 0.1 of a second, it would receive a negative penalty. This was then exploited by the bot in that it would drive just slow enough that it could tap the walls, slow down to what it needed to make the corner, and then not receive the penalty while still driving forward. Even though we had attempted to give rewards for braking, just in general, if it used the brake, it still seemed to converge on the idea that wall tapping was the best solution, which is something that's quite frustrating to see in the training episodes, as we probably did total. I personally did about 45,000 episodes, and it could only ever achieve a time of about 50 seconds on the track. The quickest time that I drove personally was 35 seconds, so obviously it's significantly slower than a human, which doesn't achieve our goal that we wanted. Okay, I'm just going to be giving a visual representation of how we are getting the gates and the data. So let's say this is the boundaries of our track. What we do is, as a driver, I am driving through the track, moving my way through, driving all the way to the end. What the record function will do, or does, is periodically it will record a position. Dot, 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 let's say every 5 or 10, you can adjust it in how you run the program. This position is an array of X, Y, Z, and importantly, the yaw. I then run a program that will generate gates that take these positions and generate a plane relative to how I drove the car. And in doing this, hopefully the bot will have enough understanding of the map, despite not actually seeing the walls. It basically only sees and it has to create its own path.
Hi, my name is Ryan, and for this assignment I took a slightly different approach to Flynn, as we were trying a few different options and working down a few different avenues. For my final design, generally I took a very similar approach to building a reinforcement learning pipeline for Trackmania. We started by creating a waypoint recorder, and we could manually drive the ideal racing line and save structured waypoint data for the track. I also constructed another model which used screen capture and LiDAR, but due to the fact that screen LiDAR doesn't correlate to environment locations and turns look like solid walls when taking a corner, that idea had to be scratched, and we went down a route which was more embedded in the game. Back to our main idea, we built a gate generator that converted those waypoints into full-width gates across the track. One important improvement I made was wall mapping. I recorded the left and right boundaries of the map and then used those wall traces to line up the gates more accurately. That mattered because relying only on the car's yaw was not always precise enough, especially around turns, so the wall mapping gave me a better way to orientate each gate to the actual shape of the track. In my final data, I recorded 102 waypoints and generated 102 gates over a track arc of about 1,178 meters. After that, I rewired the environment and reward logic so the agent was rewarded for crossing gates in sequence instead of relying on all the map-based reward methods. One of the main challenges was reliability. Gate detection could fail if the car crossed at shallow angles or moved across multiple gates between telemetry updates. To work around that, I improved the crossing logic, added gate resync behavior, and used better reward shaping with penalties for the wrong way movement, crashes, wall hits, and getting stuck. I also built the training loop using PPO, with checkpoint saving, TensorBoard logging, and testing support so the system became reproducible and runnable end-to-end. Overall, the result was a much more structured gate-based learning system. Even though we did not fully resolve every issue, especially because Trackmania behaves like a black box in some areas, the project still shows a clear pipeline from recording to wall mapping to gate generation to reinforcement learning.
I'm going to be running through how the level of achievement that we had. So I'm just basically going to set up our training scenario and just have it run just to show how we interact with it. So I'm just in my terminal within my workspace. I'm going to activate my Venv environment. And then I'm going to run my main on the port that I've set the game, and I'd set my training episode time to be about 5 million timestamps. So I run that, it begins setting up the program, it connects to the plugin socket for the actual game. I've got the connection, I will then go into my game, and it will start training. The level of how this would terminate is it determines if it isn't going to achieve enough score, but as you can see, it's doing some wall tapping to slow down as opposed to braking, which is quite frustrating to see. We were able to massively increase the training time. The limit of the actual plugin allows you to run the game at about 100 times speed. It's not very interpretable to us, like we can't really see what's going on because the frame rate just can't keep up. But what we can do is switch into the terminal and I'm getting useful data. So I'm getting how far it's getting in the map, its average reward, how it's breaking down its score. So the time cost, the wall tapping penalties that it gets, if it's getting the wrong way or if it's getting stuck, it tells me the terminate message. So crash wall hit was the last one. It's getting about 10% through the map. Its ability to achieve a time is very much how much of the entropy coefficient that it's actually using. So sometimes it'll just go through the best route. The best time it was able to achieve was about 51 seconds. I'll add a clip of that, probably running at 2x speed just to show it going through the track. But yeah, basically just involved running this a bunch of times. I wanted to explain a level of achievement that we had. We were able to run multiple instances at the same time. This effectively doubled our training speed. We were able to get twice as many episodes in the same amount of time. It involves adjusting the plugin, but it's already set up so that every new instance that you open will choose its own port, so you can run multi-threaded environments. You still run the main file, you just have to specify which ports the games are on. The games will tell you which port, but it is always going to start from 8483. That's the first port, and then sequentially it will add one every instance that you open. So if I run the environment, it'll connect to both Python sockets, it'll boot up, load the map, set the gates, and then start training. That is the extent of the project so far. I'm open to any suggestions. Please do let me know what you would suggest as a better option. The reward structure is pretty in-depth. You will be able to see that in the GitHub. But it's really, I think, the main crux of the issue of why the bot doesn't perform properly is its interpretation of the environment. It can only see those few gates. It has no other understanding of what the map actually is. It knows where it is, it knows where the gates are, but that's it. It can't see where walls are, know what block it's on, understand if it's like crashing. There's just a few limitations with the interfacing software, but again, I'm really open to any suggestions.